So the first thing we'll do is to wait a little bit, look at this minimization problem. Okay, so this minimization problem is saying I want to minimize f in x, the inner product of f minus f0, f minus f0, right? Okay, let's do some functional analysis. So the reason we want to do functional analysis is because we want to simplify this quadratic problem actually into a linear problem. So what you can say is that if I have f that actually minimized this, then if I have a for any df also in this x, okay, so the minimization statement is equivalent of saying that for any df, f plus df minus f0, f plus df minus f0, so replacing f with f plus df has to be greater than f minus f0, f minus f0, unless df is actually exactly equal to 0, right? Because if this strictly greater is not, well, let's firstly write it as greater or equal for now, right? So for any df, this is greater or equal, because if you can find a df that makes this less than, that means I should be replacing my f with f plus df, which by the linearity of the space is still in x. So this wouldn't be true anymore, right? So the minimization statement is also saying, implies that for any df, I have this inequality, right? Agreed? All right. Okay, so now let's expand this a little bit further. I can write this as f minus f0 plus df, f minus f0 plus df has to be greater or equal to this. Okay, and then I expand this. So expanding this is this term plus, okay, so I have this with this, right? Similar to how we expand products. And then next I have this with this. So df, f minus f0. And then I have this with this. So f minus f0 df plus, and lastly this with this. So the same thing as if we have just exactly a product. This has to be greater than actually the first term in this expansion for any df. All right, and that means these three terms has to be greater or equal to 0, right, for any df. And by the way, this term and this term, they are equal. So I have 2 times df, f minus f0 plus df. df has to be greater or equal to 0 for any df. All right. So that actually implies that the first term in this has to be actually exactly equal to 0. Why is that the case? Because if this term is less than 0 or greater than 0, well, if this term is greater than 0, then I can choose a negative df that makes this less than 0, right? So basically, if there exists a df that makes this greater than 0, then there also exists a df that makes this less than 0. But if there is a df that makes this less than 0, then I can always scale df to smaller values to make this quadratic term having a less magnitude than this linear term, right? And then I can always scale then, okay, So this is because if there exists a df that makes this less than 0, then there exists a very small value epsilon such that epsilon df, f minus f0 plus epsilon df, which is actually epsilon square times df, this can also be less than 0, right? Because this term scales linearly with epsilon, this term scales quadratically with epsilon. So as you make epsilon smaller and smaller, this term which is negative always wins this term that is positive. So I can always choose a small enough epsilon to make this less than 0. That means this statement cannot be true for any df, because I can use epsilon df as a df. That means the f would no longer minimize this distance. Okay, so we have proven that for f to minimize this distance, the inner product between any df and f minus f0 has to be 0. Right, so we have proven proved that f minimizes f minus f0 implies that for any df in x, df f minus f0 has to be 0. Any questions on this? So this is a way to reduce the quadratic minimization problem to a linear problem even before going into the discretization. Right? Of course you can do it the other way, but like this is more general. This makes our discrete problem a lot easier. Instead of having to solve a quadratic minimization problem in the discrete space, now we only need to solve a linear problem. All right. Okay, so this is another reason why we call the problem of finding the nearest element f in the space of x to f0 as a projection. It's because projection implies orthogonality, right? You project in an orthogonal way. And this is orthogonality. This is saying that f minus f0, or the distance, let's say projection is like, I don't know, like let's say this is f0. The blackboard is my space of x, right? The distance, then the projection of this pen to the blackboard is going to be like here, right? And then f minus f0, which is the vector that points from my pen to the blackboard, has to be orthogonal to the blackboard, right? That's what projection means. What that means is mathematically that means this vector from f0 to f has to be orthogonal to any vector in the blackboard in x. So that's what that is, right? So f minus f0 is orthogonal to any df that points into any direction in that x. So this is like f minus f0 is orthogonal to x.